This video is an introduction to solving trig equations. I'm going to go through 5 general types or common types of equations. We will learn, however, that sometimes we need to manipulate the equation first to get it to fit one of these 5 general types. Let's take a look at the first type. Type 1 is a very basic equation. I have a trig function and it's just going to be set equal to a constant once I rearrange it a little bit. Always keep in mind the domain that you're given for solving for x in this case. I'm supposed to find all the answers between 0 and 2 pi, which also means I'm in radians. So to get sine alone, I would first add the 1 to the other side and divide by 2. And we can see that sine of x equals 1/2, so I'm looking for the angles in which sine is positive 1/2 between 0 and 2 pi. Well, if you remember from our previous unit, sine is positive in both the first and the second quadrant, so I'm going to be looking for an angle in the first quadrant and another angle in the second quadrant. Let's take a brief look at our unit circle just to try and put together what we learned in the last unit with what we're doing here. I'm hopeful that you already have your answers, but just in case, we're looking for where y, because sine, remember, is y on our unit circle, is 1/2. Well, here's where y would be 1/2, and that intersects the circle in 2 different places, this point here and this point here. The angle where sine is 1/2 would be, in this case, pi over 6, which is my reference angle, and to get it into the second quadrant, you can see I'm pi over 6 radians up from the x-axis, and if I go pi over 6 radians up in the second quadrant, I would be at 5 pi over 6, because of course this is 6 pi over 6. So my 2 angles for this answer are pi over 6 and 5 pi over 6, because that is where sine is positive 1/2. If I'd been asked where sine is negative 1/2, I would have taken the answers in the third and the fourth quadrant. I would still use my reference angle. I just want to be down pi over 6 units in the third quadrant, which is 7 pi over 6, and down pi over 6 units in the fourth quadrant, which is 11 pi over 6. But because my answers are supposed to be where sine is positive, I will use my original pi over 6 and 5 pi over 6. Remember, this would be a non-calculator problem because this is one of the exact values that I know, but technically I was using sine inverse of 1/2 to get that first angle, my reference angle. If I did have a calculator problem, I would want to do the same thing on my calculator, and then I would manipulate it around the unit circle into the correct quadrants. Let's look at the second type. The second type says that I might have a squared trig function equal to a constant. You'll see as we go through this unit that oftentimes we're dealing with squared trig functions, both with expressions, which we will also learn to manipulate, and with equations. So this is another common type of equation you'll have to solve. Just as we did in the first example, we first want to get our trig function alone, and it's very similar. I will add 1 and divide by 2. And that gives me cosine squared x equals 1/2. Also, you might remember from our previous unit that when I want to square a trig function, the notation is that I put the squared symbol kind of in the middle, but this is in fact written technically like this, but it gets a little confusing, and this way you have to put parentheses, because if you don't put the parentheses, it would be confusing as to whether I'm just squaring x or if I'm squaring this whole function. So the notation that they came up with was to put the squared symbol in between so that it's clear I'm squaring this function cosine of x. When I have a variable squared equal to a constant, I always want to take the square root of both sides, so I'm going to do that same thing here. When I take a square root, I have to remember plus and minus because, of course, I could be dealing where cosine x is positive and I could be dealing where cosine x is negative because I'm squaring it. So that gives me cosine of x equals plus or minus 1 over root 2, but we know to rationalize that to get root 2 over 2, and this is another one of our exact values that we know. I'm actually looking for 4 different answers for this question because I'm looking for where cosine of x is positive root 2 over 2, that's in 2 quadrants, and I'm looking for where cosine of x is negative root 2 over 2. That's in the other 2 quadrants. So I'm actually going to have 4 values for x falling in this domain. Let's take another quick look at the unit circle. We're looking for where cosine of x, which is x on my unit circle, is both root 2 over 2 and negative root 2 over 2. That's actually not labeled on here, but if this is 1/2 and this is root 3 over 2, root 2 over 2 is in here, and you should remember that it's actually at the angle pi over 4, that cosine is root 2 over 2. Cosine is positive in the first and the fourth quadrant because those are the two values where x would be positive. Over here, this is the negative x-axis, are the two quadrants where cosine would be negative. So my reference angle is pi over 4, and that is one of my answers. The other positive answer would be in the fourth quadrant, as I said, which is at 7 pi over 4. But in fact, I need in the second quadrant, which would be 3 pi over 4, and in the third quadrant, which would be 5 pi over 4, because those are the two negative values. So I have, again, 4 answers, 1 in each quadrant. And here I've written out my 4 answers. Let's take a look at the third type. The third type says a quadratic trig equation. Well, technically, the last type was also a quadratic trig equation, but it was just one squared function equal to a constant. Here I have a quadratic trinomial, and we've always solved those a different way. We would love to factor it if it's factorable, and this is, or I might have to go to my quadratic formula, but this is factorable. It might make it easier if you rearrange it. Instead of looking at the sign values, I could just say this is similar to x squared minus 3x minus 4 equals 0, where x is equal to sine of a. That makes it a little easier to visualize, and I would factor that to be the factors x minus 4 and the factor x plus 1. But of course, it's actually sine of a minus 4 times the quantity sine of a plus 1, and those are both, when I multiply them together, equal to 0, which means either of these factors is 0, and when I set each of them equal to 0 and solve, I get sine of a equals 4, or sine of a equals negative 1. Well, you'll learn to like this type, and this first one here, sine of a, it's asking at what angle is sine 4, and we know that sine's range is from negative 1 to 1, so the sine of a could never be 4. There's no solution to this part, but sine does equal negative 1 at a certain angle, and if you remember, sine is y, and we're looking for where the y coordinate would be negative 1, and on our unit circle, that would be down here, this quadrantal angle of 3 pi over 2. However, I forgot to mention that now my domain is telling me to solve for my angles in degrees. So that would be at 270 degrees. So my answer for A in this case, would be 270 degrees. And there's only one answer here. So we've seen there can be a variety of numbers of answers. We had 2 in the first, 4 in the second, and here we have just 1 falling in this domain. Let's take a look at the fourth type. Type 4 is when you have a trig function as a common factor. And in this example, we can see that I have a sine x in both this expression and this expression. So I'm going to want to factor the common factor out. You may be thinking, well, why not just divide both sides by sine of x? But in this case, sine of x can equal 0, so you'd be dividing by 0, and in fact, you would lose some answers that way. So you're going to want to factor out the common factors for these problems. First, I've moved both factors to the left-hand side of the equation, and now when I take out sine of x from both, I'm left in the parentheses with tan of x minus 3 equals 0, times sine of x, of course. And technically, I have two factors here, sine of x and tan of x minus 3, and I'm going to set both of those equal to 0. So I'm solving for when sine of x is 0 and for where tan of x is 3. Now, unlike sine and cosine, the range for tan is not negative 1 to 1. Tan's range is actually all real numbers, so I can find the angles where tan is 3. However, it's not one of our special exact values, so I am going to need to use my calculator for this. So I'll work with this tan of x equals 3 first. Since I'm looking for the angles where tan is positive 3, I'm looking for answers in the first and the third quadrant because that's where tan is positive. I'm supposed to be finding my angles in radians from this given domain up here. And so I'm actually going to use my calculator. I'm going to do tan inverse of 3, and that's going to give me my reference angle and also one of my answers because the reference angle will be in the first quadrant and so is one of my answers. Make sure the mode of your calculator is in radians so you get the right units. And so when I do tan inverse of 3 on my calculator, I get that one value for x is 1.249 radians. And again, that is in the first quadrant, and that is one of my answers. If you remember, sorry, not great axes, but this is pi over 2, which is approximately 1.57. So 1.25, we'll call it, is somewhere here. Again, that's my answer in the first quadrant, and I'm this much up. So I now want an equivalent answer in the third quadrant, and so I want to go the same distance down. And hopefully you can see that actually I'm adding half of a revolution to my first answer, which means I'm going to add pi to my first answer to get into the third quadrant. So my answer in the first quadrant is 1.249. My answer in the third quadrant will be 1.249 plus 3.14. That gives me 4.391 for my second x value. So those are the two angles where tan of x is 3. I also need to solve for where sine of x is 0. Well, sine, remember, is y, so I'm basically looking where are the angles where the y value is 0, and that would be at 0, pi, and 2 pi given my domain because I'm supposed to include 0 and 2 pi. So over here we get 0, pi, and 2 pi. So in fact I have 5 answers for this equation. I have the 2 I got from solving the tan piece and the 3 I got from solving the sine piece. So there are 5 values for x that work with this equation. Let's now take a look at the fifth type. Remember, this is just an introduction to this topic, so of course we will be doing many more examples during class. So here's our fifth type. In general, it's when one trig function equals another. So here we have that 4 times the sine of theta equals cosine theta, and if you look at your domain, you're solving for when theta is between 0 and 360 degrees, so I'm in degrees. Now, if this equation just said, where is sine of theta equal to cosine of theta, that's one we should remember. Sine and cosine are equal, for one answer, would be at pi over 4 or 45 degrees. But this is saying, where is 4 times the sine of theta equal to cosine theta? Now, of course, I could graph y equals 4 sine of theta, and I could graph y equals cosine theta, and I could try and find the intersection points between those two graphs. But in fact, that still doesn't lead me to exact values, so I would have to go to my calculator in the end. It might be looking like this is a complicated problem, but in fact, I'm just going to combine these two trig functions to make a different trig function. So I see sine and cosine, and I know that there's a relationship between sine and cosine and tan. Tan is sine over cosine, and cotan is cosine over sine. So I'm going to rearrange this. Since the 4 is over here, I could divide both sides by sine of theta. If you want to divide both sides by cosine of theta, go for it. And that gives me that 4 equals cotan of theta. Well, we like to look at tan instead. And so I'm really saying that tan of theta would be 1/4. So I'm looking for the two angles between 0 and 360 where tan is 1/4. Again, this is not one of our exact values that we know. I'm going to need to go to my calculator, and so I'm going to do tan inverse of 1/4 to get my reference angle, and that's 14.04 degrees when I use my calculator. Remember to convert the mode of your calculator back to degrees. In the previous example, we were in radians, so you have to pay close attention to making sure your calculator is in the right mode or you won't get the right answers, which would be a shame since you're doing the right work. So as I said, my reference angle is 14 degrees, 0.04, And since I'm looking for where tan is positive 1/4, that's in the first and the fourth quadrant. So in fact, this 14 degrees is one of my answers. The other answer will be in the third quadrant. Since I'm up 14 degrees from the x-axis, I want to know what is the equivalent angle in the third quadrant that is down 14 degrees. Well, again, you can see if this is 14, I need to add 180 degrees now because I'm in degrees. I need to add 180 degrees to 14, and that will give me my next answer, which of course is 194.04 degrees. I want to talk about if this had said tan of theta equals negative 1/4, because we're going to learn that in your calculator, you will still find the reference angle. So you will ignore the negative. Trust me that sometimes it works out when you put the negative in with some functions and sometimes it doesn't. It's better to just be consistent. So always find your reference angle by finding the positive, and then if this had been negative 1/4, I would just move it to the appropriate quadrants. Again, we'll practice that in class. So there are two answers for theta here. I guess I should finalize that by saying theta equals 14.04 degrees and 194.04 degrees. I hope this video was helpful, and we'll do many more examples in class.